Welcome to physics class. My name is Gias Uddin. My dear students, today we are going to discuss about some important problem based on Heisenberg uncertainty principle. Today our part number 3 based on Heisenberg uncertainty principle. Okay. So our first numerical problem is estimate the uncertainty in the position of number A, a neutron moving with a neutron particle moving with at 5 into 10 to the power 6 meter per second. And part B, number B, a 50 kg person moving at 2 meter per second. So this is our first numerical problem. The statement of this question: estimate the uncertainty in the position of number A neutron particle moving with speed 5 into 10 to the power 6 meter per second, and number B, a 50 kg person moving at 2 meter per second. Okay, solution of the question. Solution given for neutron particle as we know that mass of neutron equal 1.67 into 10 to the power minus 27 kg, and Planck constant 6.62 into 10 to the power minus 34 joules second, and delta B equal uncertainty in velocity 5 into 10 to the power 6 meter per second, 10 to the power 6 meter per second. Calculate the uncertainty of position. Okay, so delta x equal what? We need to find out delta x. Okay, so we know that by using Heisenberg uncertainty principle, delta x into delta p greater than equal h squared by 2 equal h by 4 pi. Okay, and delta x equal delta p equal h by 4 pi, and this is equal to delta x, and delta p we can break in terms of mass into delta b. This is equal to h by 4 pi. Okay, and delta b equal h by 4 pi m into delta b. Okay, now delta b equal the value of h equals 6.62 into 10 to the power minus 34, and 4 into the value of pi equal 3.14, and mass of neutron particle equal 1.67 into 10 to the power minus 27 into delta b. This is equal to 5 into 10 to the power 6. 5 into 10 to the power 6. So this is equal to, after solving this part, this is equal to, sorry, this is delta x equal 6.4 into 10 to the power minus 15 meter. So this is our required answer, uncertainty in position. Okay, now we are going to second part. Now we are going to solve second part. Okay. For person mass of person equal 50 kg and uncertainty in speed or velocity delta b equal 2 meter per second. Also Planck constant h equals 6.62 into 10 to the power minus 34 joule second. Okay. And delta x equal what? Again, we can apply Heisenberg uncertainty principle. We know that delta x into delta p greater than equal h cross divided by 2 h by 4 pi. Okay. So delta x into delta p we can break in terms of m into delta b, and this is equal to h by 4 pi. Okay. And delta x equal h divided by 4 pi m into delta b. Now delta x equal the value of h equals 6.62 into 10 to the power minus 34 and 4 into 3.14. Mass of the person 50 kg. Okay. And delta b, this is equal to 2 meter per second. 2 meter per second. Okay. After solving this part, we will get 2.0, 20.0, 20.5 into 10 to the power minus 36 meter. So this is our required result, uncertainty in position of the person. Okay. Okay, our next numerical problem is this. The statement of this problem: find the lowest energy of a neutron particle confined to a nucleus of size 10 to the power minus 14 meter. So confined of a nucleus of size 10 to the power minus 14 meter. So this is clear that this is uncertainty in position. Okay. So the given information of this question, given delta x equal 10 to the power minus 14 meter. Delta x equal 10 to the power minus 14 meter and Planck constant 6.62 into 10 to the power minus 34 joule second. Okay. And mass of the Newton particle equal m equal 1.67 into 10 to the power minus 27 kg. Okay. First of all, we are going to find out delta p. So by using Heisenberg uncertainty principle, we know that delta x into delta p greater than equal h cross divided by 2 equal h by 4 pi. Okay. So this is equal to delta x into delta p. This is equal to h by 4 pi and delta p equal h by 4 pi into delta x. Okay. Delta x. Now delta p equal the value of h equals 6.62, Planck constant 6.62 into 10 to the power minus 34 and 4 into the value of pi equal 3.14 into delta x. This is equal to 10 to the power minus 14. After solving this part, we will get 1.04 into 10 to the power minus 20 kg meter per second. Okay. Again we know that E equal mc square. This mc square we can rearrange in terms of mc into c, and we know that mass into velocity, this is equal to momentum, so we can write p into c. P minimum into c, okay. So this is equal to, see, this is the speed of light in vacuum. So this is delta p and p minimum, this is equal to each other. So we can write 1.04 into 10 to the power minus 20 into speed of light 3 into 10 to the power 8. After solving this part, we will get 3.12 into 10 to the power minus 12 joule. Okay. So the minimum energy is equal to 3.12 into 10 to the minus 12 joule. Thank you. Listen. Okay, our next numerical problem is the statement of this problem. A hydrogen atom has a diameter of 0.53 angstrom. Estimate the minimum energy an electron can have in this atom. Okay. Solution of this question. The given information of this question, solution. This is uncertainty in position. So delta x equal 0.53 angstrom, and this is equal to 0.53 into 10 to the power minus 10 meter, because we know that angstrom is not SI unit of the length or distance, so it should be converted in SI system. So we know that 1 angstrom equal 10 to the minus 10 meters, so we can write 0.53 angstrom equal 0.53 into 10 to the minus 10 meter. Okay, and also Planck constant H equals 6.62 into 10 to the power minus 34 joule second. Okay, and first of all we are going to find out we know that by Heisenberg uncertainty principle, delta x into delta p greater than equal h card by 2 equal h by 4 pi. Okay, so delta x into delta p, and this is equal to h by 4 pi, and delta p equal h by 4 pi into delta x. Okay, now delta p equal the value of h equal 6.62 into 10 to the power minus 34, and 4 pi 4 into 3.14 into delta x, this is equal to 0.53 into 10 to the power minus 10. After solving this part, we will get result is 9.94 into 10 to the power minus 24 kg meter per second. Okay, now we are going to find out again minimum energy. Estimate the minimum energy. Yes, so E minimum equal P square divided by P minimum divided by 2m. Okay, so the value of P minimum, this is equal to delta P. So the value of delta P equal 9.94 into 10 to the power minus 24, and 2 into particle is electron, so 2 into 9.1 value mass of electron equal 9.1 into 10 to the power minus 31. After solving this part, we will get 5.43 into 10 to the power minus 19 joule. So this is our minimum energy, required minimum energy. For your better understanding, I am going to repeat this once again. The statement of this question: a hydrogen atom has a diameter of 0.53 angstrom. Estimate the minimum energy an electron can have in this atom. Okay, so the given information of this question, 0.53 angstrom, this is the uncertainty in position, so we can write delta x equal 0.53 angstrom, and this is equal to 0.53 into 10 to the minus 10 meter, because we know that 1 angstrom equal 10 to the minus 10 meter, and Planck constant 6.62 into 10 to the minus 34 joule second. By using Heisenberg uncertainty principle, we can write delta x delta p greater than equal h cross divided by 2 equal h by 4 pi, and delta x delta p equal h by 4 pi, and delta p equal h by 4 pi into delta x. When all the values substituted in this equation, then we get 9.94 into 10 to the minus 12, 24 kg meter per second. Again, we know that E minimum equal P minimum, P square minimum divided by twice m. When the value of P substituted in this equation and 2m, it means that mass of electron 2 into 9.1 into 10 to the minus 31 kg. Okay. After solving this part, we will get E minimum equal 5.43 into 10 to the minus 19 joule. Thank you. Okay, our next numerical problem is this. The statement of this problem: compare the uncertainties in velocity of a proton and electron. There are two particles, one is proton and there is electron. Okay, so compare the uncertainties in velocity of proton and electron contained in 2.0 angstrom box. Okay, so 2.0 angstrom, this is uncertainty in position. Okay, so the given information of this question, solution, given delta x equal 2.0 angstrom, and this is equal to 2 into 10 to the power minus 10 meter, because we know that 1 angstrom equal 10 to the minus 10 meter. Okay, and Planck constant H equals 6.62 into 10 to the power minus 34 joule second. We need to find out delta BP divided by delta BE equal what? Okay. First of all, we are going to find out delta B. We know that delta P into delta X greater than equal H cross divided by 2 equal H by 4 pi. Okay. H by 4 pi. And again delta P into delta X equal H by 4 pi. And this is equal to delta P equal H by 4 pi into delta X. Okay. So in this term, we can say that H is Planck constant, 4 pi is constant, and delta X are constant for both particle photon and electron particle. Okay, that means uncertainty in position for photon and electron are same. Okay, so we can write delta P. Now, delta P directly proportional to 1 by B. Sorry, delta P we can break M into delta B. Sorry. We know that delta X into delta P greater than equal H cross by 2 equal H by 4 pi. Okay, and delta X equal delta P we can break in terms of M into delta B, and this is equal to H by 4 pi. Okay, and delta X equal delta B equal H divided by 4 pi M into delta X. Okay, in this term we can say that H is Planck constant, 4 pi is also constant, and delta X constant for both particle photon and electron. So we can say that from this equation delta B directly proportional to 1 by M. Okay, so we can write delta B P divided by delta BE, this is equal to ME divided by MP. Mass of electron, this is equal to 9.1 into 10 to the power minus 31, and mass of proton 1.67 into 10 to the power minus 27. So we know that mass of electron, this is equal to 9.1 into 10 to the power minus 31 kg, and mass of proton is equal to 1.67 into 10 to the power minus 27 kg. Okay, so after solving this part, we will get 5.449 into 10 to the power minus 4. So this is our required answer, delta BP divided by delta BE. This is the ratio between uncertainty of proton and electron in the case of speed or velocity. Okay, so this is our required answer. Thank you. Okay, our last numerical problem is the statement of this problem: wavelength can be determined with accuracies of 1 part in 10 to the power 6. What is the uncertainty in the position of 1 angstrom X-ray photon when its wavelength is simultaneously measured? Okay, so 1 angstrom, this is uncertainty in position, this is clear that. Okay, and the solution given wavelength can be determined with accuracies of 1 part in 10 to the power 6. So we can write delta lambda equal 1 by 10 to the power 6. Okay, and delta X equal 1 angstrom, and this is equal to 10 to the power minus 10 meter, and Planck constant also 6.62 into 10 to the power minus 34 joule second. By using Heisenberg uncertainty, we know that delta X into delta P greater than equal H cross divided by 2 equal H by 4 pi. Okay, so we can write delta X into delta P equal H by 4 pi. Delta P we can arrange in terms of delta X into H divided by delta lambda square into delta lambda equal H by 4 pi. Okay, H and H cancel to each other. So we can write delta X into delta lambda divided by lambda square equal 1 by 4 pi. And delta X equal delta x equal delta x into delta lambda divided by lambda into lambda divided by 4 pi. Okay, so delta lambda divided by lambda equal 1 by 10 to the power 6. Okay, so delta x into 1 by 10 to the power 6 equal lambda divided by 4 pi. 4 pi. Now delta x divided by 10 to the power 6 equal lambda divided by 4 pi. 4 pi. Okay, now delta x equal delta x divided by 10 to the power 6 equal lambda divided by 4 pi, and this is equal to delta x equal lambda divided by 4 pi, lambda equal 10 to the power 10 angstrom. Okay, 10 to the power minus 10 angstrom divided by 4 pi. Okay, sorry, into 10 to the power minus 10 divided by 4 pi, and this is equal to delta x divided by 10 to the power minus 4 into 4 pi, and this is equal to, after solving this part we will get, that means we can write 10 to the power minus 4 into 4 into 3.14, and this is equal to 7.96 into 10 to the power minus 6 meters. So this is our required uncertainty in position. Thank you.